So, Markov chains are used to model a wide array of real-world phenomena. And as I've alluded to before, in statistical modeling, we create mathematical abstractions, or models, which replicate features of real-world processes which we observe. We then collect data by recording observations, so in the case of Markov chains, just a sequence of discrete states, which we then marry with our mathematical abstraction, in this case a parameterized transition probability matrix, via a so-called likelihood function. Now we'll cover likelihood inference later on, but an assumption that is often imposed on such models is that of so-called stationarity. And we model the observed process using a stationary Markov chain. Now there's more to this than we'll cover here, but very loosely speaking, this means that for a process initiating under the so-called stationary distribution, remember that the initial distribution is just a marginal distribution, the process will have the same distribution over subsequent time steps. Now, indeed, when we construct models which account for any uncertainty in observing the initial state of the process, we include this stationary distribution directly in the calculation of the likelihood function. Again, more on this later. Another assumption that is often both of theoretical and practical use is that of reversibility. As the name suggests, this is an assumption that imposes probabilistic structure on the transition matrix of the model process, which ensures that the process behaves statistically the same way it does running backwards in time as it does forwards in time. Now, this is of notable importance in fields such as chemistry, for example, where reversibility is critical for adhering to basic laws of thermodynamics. Indeed, recently I've had the privilege of working on reversibility for Markov chains with a friend of mine, Professor Ian MacDonald, and I'll include a reference to a paper shared with us during communication with us by someone who knows a bit more than we do about so-called ion channel kinetics modeling, where reversible Markov chains find application, albeit in the continuous case. And it's really interesting stuff. I'll also include links or references to a recent paper of ours which covers modeling with discrete time Markov chains under the assumption of reversibility if you're interested in just the modeling aspect itself. So for today's video, we'll start off by defining the limiting and stationary distributions and how to derive these, and then we'll venture into these so-called detailed balance equations and checking for reversibility. So let's jump in. So consider again calculating the t-step transition probabilities for a Markov chain starting from some initial distribution, say delta naught, but over a long transition horizon. So we apply our updating equation for calculating the marginal distributions, and we evaluate delta t transpose, so there's the marginal distribution at time t, as being equal to delta naught transpose post multiplied by gamma to the power t, where gamma is the one-step transition probability matrix. And obviously gamma to the power t is the t-step transition probability matrix. Now, for certain specifications of the transition matrix, we observe that as the transition horizon t increases, the marginal probabilities tend to stabilize. Furthermore, we note that this behavior occurs regardless of our choice of initial distribution, and these long-run probabilities always converge to the same values. So this means that over sufficiently large transition horizons, probabilistically speaking, the distribution of the process over the states it may assume is the same regardless of where it starts. Now, this is the premise behind the so-called limiting distribution of a Markov chain. Okay. Now, noting that this behavior is determined by the behavior of gamma to the power t, so the t-step transition probability matrix, formally we state that a unique limiting distribution, which we will denote as boldface pi, is given as the limit of t as it tends to infinity of gamma to the power t, so the t-step transition probability matrix, and that being equal to a column vector of 1s post multiplied by this boldface pi transpose. Okay, so what this means is that in the limit, gamma to the power t, so the t-step transition probability matrix, converges to a matrix with identical rows. Now, depending on the specification of the transition probability matrix, this limit may or may not exist. And when referring to the limiting distribution, one should, as in the case of any other mathematical sequence, think of it as a set of values which is approached as the sequence of probabilities develop, and thus treat such values with the usual scrutiny where existence of a limit to infinity is concerned. But fortunately, if such a distribution exists, it is unique. So there will only be one set of values you could assign to that limit. When it does not exist, closer scrutiny of the series may still yield useful insight on the behavior of the chain. So all is not lost, but in general, care needs to be taken when assigning values to the limiting distribution. And I'll include a little homework exercise for you to demonstrate the point. So a stationary or invariant distribution is defined as that marginal or unconditional distribution which is invariant under the operation of the transition matrix. So that is, if we denote the stationary distribution by boldface delta, note that we just dropped the time argument here to indicate the time invariance, then it is given by that vector delta, which satisfies delta transpose equals delta transpose gamma, where gamma, of course, is the transition probability matrix. Subject, of course, to the condition that delta is a distribution, so its elements must sum to 1. Now, recalling the calculation of marginal distributions over a single time step, the popular nomenclature of invariant distribution becomes clear, since the operation when applied to a stationary distribution simply regurgitates that same distribution. Another way to interpret this equation is to think of the process as being in some form of statistical equilibrium. Indeed, this set of equations which define the stationary distribution is often referred to as dictating so-called global balance. Now, at this stage, it's probably worth contrasting stationary distributions with limiting distributions, as it's easy to get the two confused, and consequently also the theory which applies to either case when conducting analysis. We note that the limiting distribution, if it exists, is always a stationary distribution. Okay, so simply post-multiply the limiting distribution by a transition matrix to see why this is the case. So that is, the limiting distribution will satisfy the equations which define a stationary distribution. But the converse is not true. The stationary distribution is simply that which satisfies the present set of equations. The limiting distribution is defined by values which you assign to an expression in the limit. These need not be the same thing. Okay. Stationary distributions also need not be unique. So for reducible Markov chains, for example, there may be numerous or possibly an infinite number of such stationary distributions. So again, a good understanding of the implications of qualitative properties such as irreducibility and the structure of a model chain goes a long way in the application of assumptions such as stationarity where real-world processes are concerned. Now, calculating the limiting distribution involves evaluation of a limit over a non-finite transition horizon, which necessitates a general expression for the t-step transition probability, or at least an analysis of the resulting sequence of probabilities as t increases. Sometimes this is easy, sometimes it is not. Fortunately, calculating the stationary distribution is rather straightforward. We simply combine the expression which defines the stationary distribution with the constraint that the probabilities sum to 1, since it's a distribution, in a single set of equations. And we combine these as follows. We state that delta transpose, where delta of course now indicates the stationary distribution, post-multiplied by a matrix which is constructed by taking the transition matrix, so the one-step transition probability matrix with a column vector of 1s, must equal a row vector constructed by taking delta transpose by a scalar 1. Okay, so this system defines a set of equations which we can solve for the stationary distribution. Okay, so remember delta is the thing we're looking here for. And we note that we need only u of these equations, where u again denotes the number of states that the process may assume, to solve for the stationary distribution. So you can actually remove one of these equations and solve the resulting system. And that's how you get the stationary distribution. Alternatively, what we can do to calculate the stationary distribution is we may use the following result, which I've adapted from Zucchini, MacDonald, and Langrock, it's their textbook, which is that the vector delta, so again the stationary distribution with non-negative elements, is a stationary distribution with transition probability matrix gamma, if and only if the following is satisfied. Now that is that delta transpose by a post-multiplied by a matrix, which is constructed by taking the identity matrix minus gamma plus u, where u is just a matrix of the same size as gamma, populated with a number with 1s, is equal to a row vector of 1s. Okay, so this again gives us a system of equations which we can solve for delta. And as you can see from the structure of that system, maybe it's a bit easier to solve. Obviously, also thanks to the if and only if, we can use the same system to verify whether a vector is a stationary distribution or not. So earlier I remarked that qualitative decomposition of Markov chains allows us to infer distributional properties of a Markov chain without the need to resort to complicated calculation. The complicated calculation I was referring to there being things like t-step transition probability matrices and generating functions for first return. Indeed, when we looked at the decomposition theorem, we saw that we could actually make assertions about things like transience and recurrence simply with reference to the transition diagram, which were essentially statements about the distributional properties of the process with respect to the time domain, so first return. However, qualitative decomposition has implications for the limiting and stationary distributions as well, i.e. its so-called long-run distributional properties. Consider the following theorems. An irreducible Markov chain will have a unique limiting distribution with non-zero entries if and only if all states are aperiodic and positively persistent. So, if we can establish that a chain is ergodic, we can then infer that it has a unique limiting distribution. So one set of values that you could assign to that limit. And again, consequently, a unique stationary distribution. Next theorem. An irreducible Markov chain with positive persistent states will have a unique stationary distribution. So note that we do not require aperiodicity for uniqueness of the stationary distribution. That is a requirement we had for the limiting distribution, but not for the stationary distribution. So, if we establish that a Markov chain is irreducible, then we know there will be a unique stationary distribution. Recalling what I said earlier about it being possible for a chain to have multiple stationary distributions, which incurs caution on the part of the statistician in practical applications, this is clearly a useful result, since one can assert that when you find the stationary distribution for an irreducible chain, it is the stationary distribution. As a final note on the implications of qualitative decomposition for Markov chains, we note the relationship between the limiting probabilities, the stationary probabilities, and the mean first return time. Okay, so let mu jj denote the mean first return to state j. Then we have that if state j is aperiodic, then the limit as t tends to infinity of the t-step transition probability from state I to state j is just equal to the jth element of the limiting distribution. Okay, so pi j, which is also equal to 1 divided by mu jj, so the mean first return time. Also, if state j is periodic with period d, then we have the limit as t tends to infinity of the probability of transitioning from state I to state j in d times t steps is just equal to d times the jth element of the limiting distribution, which is equal to d divided by mu jj. So, in consequence, if we establish that a chain is ergodic, then we'll have a unique limiting distribution, which will also be the stationary distribution. And thus, once we determine that distribution, we can use this relationship to calculate the mean first return time directly from the stationary distribution. Now, as you may note from earlier exercises, this is much easier than finding the appropriate generating function for the first return distribution. Okay. Now, in the case where the chain is periodic, Ross et al. Notes, and I have to clarify that this is after stating that delta will still satisfy the equations which define the stationary distribution, and I paraphrase. But now delta j must be interpreted as the long-run proportion of time that the Markov chain is in state j. Thus, delta j is equal to 1 divided by mu jj, whereas the limiting probability of going from state j to state j in t times d steps is just given by the limit as t tends to infinity of the probability of transitioning from state I to state j in d times t steps, which is equal to d times delta j, which is equal to d divided by mu jj. Okay, so the implication of this last statement is that, well, regardless of the periodicity of the chain, we may use the stationary distribution to infer the mean first passage time. But note the first subtle difference in interpretation. So another important concept as it relates to stationarity is that of reversibility. So MacDonald and Pinar write. Actually, as you'll be able to tell from the extra writing, this is mostly Ian's writing. But here goes. If it is known or suspected that the phenomena under study is invariant under reversal of time, one has to be able to fit a model reflecting that property. That is, the finite dimensional distributions of the fitted process should also be invariant under reversal of time. They should not permit the possibility, for instance, that some quantity may go up by the stairs and down by the elevator. That's a quote by Martin and Ross. And even if one suspects irreversibility, also known as directionality, it may nevertheless be informative to fit a reversible model in order to compare it with one permitting irreversibility, so directionality. Indeed, reversibility shows up in the analysis of numerous real-world processes, in fields ranging from chemistry and physics to statistical finance, and often one has to impose reversibility in order to construct or in order to conduct sensible analysis. Okay. Now, the intuition behind reversibility is that the process looks the same running backwards in time, statistically. Okay, so to see what that means, I will cover the definition first and then come back to that. Okay, so a Markov chain is said to be reversible with respect to some distribution, which we will denote boldface nu, if it satisfies the so-called detailed balance equations. And that is that nu I, so the ith element from that distribution, multiplied by gamma ij, so that's the ijth element of the one-step transition probability matrix, equals nu j times gamma ji. And that set of equations needs to be satisfied for all pairs I and j. Okay, now you can actually write that entire set of equations in matrix forms as follows. You take diag nu times gamma is equal to gamma transpose post multiplied by that same diag nu. Okay, where diag nu just denotes a square matrix with diagonal entries given by the vector nu. Okay, so all of the elements on that diagonal. If a process is not reversible, so i.e. when it does not satisfy detailed balance, then it is said to be irreversible or directional. Now, just a quick side note, but boldface nu is necessarily a stationary distribution. Now, this is a statement which I've left for proof as an exercise, since it follows directly from the detailed balance equations. Okay, so you should be able to figure it out on your own. So to see how this all relates to the statement looks the same running backwards in time, consider the statistical properties for the reverse process. Okay, let's take the probability of the process being in state I at time t minus 1 and being in state j at time t, and let's decompose it as follows. Write it as the probability of the process being in state I at time t minus 1, given that it was in state j at time t, multiplied by the probability of being in state j at time t. Okay, now note the direction of the time there. We're moving backwards from j to state I. Okay. Alternatively, we can take that exact same probability and we can again write it as a conditional, but forward in time, right? So we can write it as the probability of being in state j at time t, given that the process was in state I at time t minus 1, and then of course multiplied by the probability of being in state I at time t minus 1. Okay, so moving forward from state I to state j. So the process will thus look the same running backwards statistically if the marginals are from stationary distributions. Those stationary distributions are the same for the forward and backward process, and if the transition probabilities for the process are gamma ij running forward and gamma ji running backward, i.e. if detailed balance is satisfied. Indeed, Ross et al. Writes, the condition for time reversibility can be interpreted as stating that for all states I and j, the rate at which the process goes from state I to state j is equal to the rate at which it goes from j to I. Okay, so the go up by the stairs and down by the elevator quote from Martin and Ross should now be more clear, right? It's about how fast you go in either direction. In closing, reversibility is a fascinating subject, and it doesn't only pertain to Markov chains. Indeed, it's an important concept which you should no doubt run into again in your studies on stochastic processes. But until we get to inference for reversible processes in the present context, what's most important for you to know is how to check for reversibility, i.e., if I give you a distribution and a transition probability matrix, can you check if detailed balance holds? Alternatively, what I can do is I can just ask you to check if a chain is reversible, and you need to figure out on your own what distribution to check. Cool, so I hope you found that interesting. As usual, I'll leave some homework problems for you to check out, and then I'll see you in the next one.